Hello reviewers, welcome to my show Future Friday. In today's episode we're going to take a look at superconductors. So let's dive right into it. Now first thing you have to understand, electricity has resistance as an inherent aspect of it. So you must be familiar with the aspect of voltage, how many volts it is, and current, like how much energy is going from one place to another. Voltage is what allows it to go. So voltage is like, go from point A to point B, potential difference, and then you have current that is doing the work. Now problem is that every conductor that we have has inherent resistance to it, and that creates a problem that we cannot control resistance. The only way we can control resistance is basically make the cable thicker. We can't control it. Like let's say somebody says you, hey, tungsten wire has this much resistance, let's say it has 100 ohm resistance, can you make it higher? Let's say you, for some reason, for some electrical purpose, you need it, let's say 10,000 ohms rather than 1000 ohms. Yes, deal, you can make it thinner. It will become basically far higher resistance. But to make it basically go down in resistance, we can't do that. We simply have to add more to it. So that is what the biggest problem. And resistance is literally waste of energy, because resistance is not doing anything for you unless you are designing resistance in your chips. Then it's not doing anything. Like the resistance of your conductor wire that is in your home, that's not doing anything. Resistance in the transmission line, that's not doing anything. So in those sort of scenario, it's just wasteful. And on top of that, that waste is not just magically converted into something harmless. It's converted into heat, which at high enough current can, you can see, it can melt things. So you have to understand, it's not that we can just let it go to waste, because it will harm the conductor, it will harm the insulator. Worst case scenario, it can set your home on fire. So we have to take care of electrical resistance. So right now the only thing we do is just simply make the conductor thicker. So superconductivity is this idea, is that there is a state in some materials. The material is what we call superconductor. So that's why please be aware of it. There are two things, superconductivity versus superconductor. So superconductor at a certain temperature simply goes to zero. It's like zero, absolutely no resistance. And I mean that as in there is no resistance that is measurable by any stretch of the imagination. You can't mathematically measure it. It's not that, oh, it's 0.000000017 micro ohm. It's not like that. It's not there. It's physically not there. Now you have to understand, when we are talking about things that is cooled down to very cold degrees, everything becomes a very good conductor. As you can see by this graph, it's like everything is going to basically more and more conductivity. But the idea was it should reach to zero, as in the resistance should reach to zero when we reach absolute zero in the Kelvin scale. Basically the coldest we can go, absolute zero. But the idea with superconductor is that instead of basically waiting for absolute zero to arrive, it hits zero resistance before it. So that before it is what we call a critical temperature. So basically if you reach that temperature, it will say, okay, now you don't have to cool me down any further, I'm at zero resistance. That's the critical aspect, because more or less everything becomes superconductor if you cool it down to 0 Kelvin. Superconductors are the conductors that can do it at much hotter temperature, and at this scale temperature are measured in Kelvin, not in Celsius, not in Fahrenheit. They are measured in Kelvin. And you have to understand this person, his name is very hard to pronounce, I'm sorry for that, Heiken Karma Hein Owens, I cannot pronounce it, but it was found upwards of 100 years ago, April 8 in 1911. So you have to understand, and he was experimenting with mercury, and this guy is the reason why we figured out basically how to make liquid helium. That is the coldest fluid that we can make, and that allows to research on these front. Liquid nitrogen is cold, but liquid helium is like hold my beer. So liquid helium is very cold. That allowed these kind of experiments. So when he was experimenting with mercury, and he was like, okay, at 50 Kelvin it's this, at 30 Kelvin is this, at 27 Kelvin, oh wait a minute, is zero. So the graph simply went coming down, and zero. So this aspect, like hitting zero resistance before you reach 0 Kelvin, is superconductor. Superconductivity is a state of superconductor where you have cooled it, because you can have what you call superconductor in your hand. It simply won't be conducting anything, because unless you cool it down, you're gonna melt it if you try to pass electron through it. So understand, superconductivity is a state, superconductor is what allows it once you cooled it down. So these two are completely different. So how cold? When we are talking about cold, okay, it's just cold. How cold? To give you a context, I already specified it must be measured in Kelvin, because in degrees Celsius or degree Fahrenheit, it's way too confusing. To give you a context, we are all familiar with ice. So ice is at 0 degrees Celsius. Simple, common. Now here's the, in Kelvin scale, this is upwards of 273 Kelvin. Yeah, it's 200 degree in Kelvin scale. So basically Kelvin scale is a degree Celsius scale, just move down to absolute zero. It counts from absolute zero. So that's your idea. So 0 degrees Celsius, we are all familiar with it. Now many of you may have seen dry ice that goes up to minus 78 degrees Celsius. Now in Kelvin scale, that's 194. So it's still in triple digit. Then you come to liquid nitrogen. Some of you may have seen this. And that goes to upwards of minus 196 degrees Celsius, and that only goes to 77 Kelvin. And then you need liquid helium. The coldest we can ever reach is minus 270 degrees Celsius, and it is upwards of 4 Kelvin. Now be mindful when you say people are experimenting with zero gravity, absolute zero, is that they are never going to absolute zero here. They are going to micro Kelvin, nano Kelvin, but they cannot go to 0 Kelvin. Physics does not allow that. So that is why I'm like giving you a rough temperature. Like if you have just normal garden variety liquid helium, it will be upwards of 4 Kelvin. So understand that, like, it's very cold. The temperature that we are talking about is unperceptible to us. Like even the basically material or fluorine gas that is in your compressor, or some greener alternative that you have, that also goes to barely minus 20 or 30 degrees Celsius. That's why you can make ice creams which are like minus 18 or 16 like that. But dry ice is very cold. This is at this temperature is dangerous for humans. Liquid nitrogen, it's lethal to human. Liquid helium, you dead. So understand, when we are talking about this temperature, it's not something easy to achieve. It's not something easy to maintain. And again, liquid nitrogen, you can understand, the flask that can handle liquid nitrogen costs more than $10,000. Now of course, good quality one and big capacity one, you can buy a few $100 small one. So this is the aspect of it's measured in Kelvin, and it goes to very low temperature, minus 270 degrees Celsius. It's very cold that we are talking about here. So, okay, you might be like, there is superconductor, then why do I care? Here's the deal. It allows us to save lives. MRI machine is direct descendant and directly made possible because of superconductors. If we try to make MRI machine without superconductor, can we do it? Yes. There will be few problems with that. First, the electrical consumption would require the hospital to be next to a power plant. On top of that, it will be ludicrously huge. On top of that, it will not allow high enough resolution. Basically, the slices that you see a MRI machine making won't be high resolution, it won't be clear enough. Will it still work? Yes, but will it be good enough to actually do anything? Most of the time, no. Of course, it will be better than nothing, but if you want life-saving MRI, you need to have a superconducting MRI. Almost 100% of them are superconducting. So they are generally running on liquid helium. So many times you see a MRI room and there would be a refrigeration room independent from it, where they are handling the liquid helium aspect of it. And that's very important for us, for you and I. Basically, if you can figure out how to make superconductor cheap or lightweight enough, or that is more resilient, more affordable, MRI machine cost will go down. And if MRI machine will cost go down, you can save more lives. Imagine a hospital, instead of having 2 MRI machine, having 200 MRI machines. You can save a lot more life very quickly. So it's not something that is only scientists and lab coats are dealing with this. This is life threatening for us. So if we figure out how to make good MRI machine cheap, effective, that does not require a power plant, that's awesome. Then of course advanced science is there. Now if you can't make out what this is a quantum computer. Don't think too much about it. It's just it's on a level that is very complex, very dizzying kind of scenario. Basically you have binary in your computer which has on or off. This has 8 qubits. Basically every byte in this has 8 states. It's not that on or off, it has 8 states into this. So it's completely different ballgame. So a lot of advanced science is possible because of superconductors. So this is the aspect we need it. It's not something that okay, whether I have it or not have it, it makes a very huge difference. Now there is a problem to it. Now the first problem many of you have easily guessed is cost, undeniably. So these things are very, very ludicrously expensive, because not only the material, let's say even if the material is very cheap, it creates a problem that how do you insulate liquid helium? It's not something that you can just easily do. If you try to do it with steel, it will shatter steel, and I mean low temperature steel, it will shatter. So you have to figure out something that can handle that temperature. Now many things can handle that temperature. There are certain alloy that can handle that. Here's the deal, they are not flexible. So you can say if you're making a cable or conductor out of it, you have to take into consideration the insulation that you need to make sure liquid helium remains in liquid state. That's not easy. So you may have a scenario where the conductor is almost like, let's say, $10,000 per kilo, but the insulator will cost you more than that. So that happens. You have to understand the cost is very high. On top of that, temperature, like this is a refueling of basically MRI machine. As you can see, like it takes upwards of 1,000 liters of liquid helium. It's not cheap. And the refrigeration room that I specified, that's just there to make sure it maintains it. It's not there to refill it, it's just there to maintain it. So you can understand the temperature is very low. Like the amount of temperature that these puppy reach is so low that if you try to make MRI machine in top floor of a building, it simply won't work because it's getting more of a solar radiation. Now it simply means it will evaporate helium much more quicker, and you have any radio frequencies or things that also can heat things up. So it's not that your MRI machine won't work, it's simply you have to refill it very quickly. So you have to understand at those low temperature, everything affects everything. So you can have somebody dialing up a mobile phone, and it's like that signal, that few watts of signal can start to heat up helium. It's that low temperature. It's mind-boggling what kind of difficulty engineers have to deal with. On top of that, it also has capacity limitation. Now this aspect I really want you to understand, pay close attention to, is that when somebody shows you like, okay, this is my conductor, copper conductor, and this is my very small superconductor. Now yeah, that's true, but superconductor has zero resistance. That means no matter how long you make it, it will not have any loss. Now there would be microscopic loss, there always is due to uncertainty principle, but it will be negligible. Let's just put it that way. So if you have 1,000 kilometer of superconducting conductor transmitting power from, let's say, power plant to substation, yeah, of course there will be some loss, but it would be like, let's say, for you are sending 12,000 megawatt, your loss would be barely 1 or 2 kilowatts. So that's amazing. Right now we lose upwards of 5 to 3%. So that's a lot of however, it does have a limitation, as in if you see this bundle of cable, they are rated at 12,500 ampere. Now this is a superconductor, it's also rated at 12,500 ampere. Now here's the deal, why the heck it has a rating? This is what I want you to focus on. Even though superconductor does not have a resistance limit, it does have a maximum saturation limit. Basically, if you try to pass more than 12,500 ampere through it, it will lose its superconductivity. So you have to be below it. Understand this. Because most of us are familiar with the aspect, you can overcurrent. Basically, you have a conductor, you can overcurrent it for a while, it will just heat up. In superconductor, if you overcurrent it, it simply loses its superconductivity. So you cannot overcurrent it. So be aware, it does not mean you can have, let's say, one cable, let's say from China has the longest high voltage DC lineup. You can check my video about high voltage DC here, and that's transmitting 12,000 megawatt of power. But let's say in future they want to upgrade it and add, let's say, even 100 megawatt. They have to either redo the superconductor line or send that 200 megawatt or 400 megawatt externally, because this does have a saturation limit and you have to be below it for safety reasons. So there are certain problems with it. Let's say you paid for the cost. Let's say you can handle liquid helium. It still has a capacity limit. So if you want to run a country through let's say you have a giant wind farm in, let's say somewhere out of the coast, and sea-based wind farms, yeah, it can provide more than enough power and it will work, but you still have to have a very thick superconductor. Yeah, it will be 100 times smaller than compared to a copper conductor, but still would be big. It won't be like, oh, I have a thread of it and I can transfer as much power as I want. They still has a limit. So what we can expect in the future? Now, if you type superconductor, the first thing you will see is warm temperature superconductor. Now, this is why I want you guys to pay attention to the Kelvin scale, because warm in Kelvin scale simply means liquid nitrogen. Oh, it's in double digit. Oh, it's in 70 degree Kelvin. Yeah, it's warm. So that's why do not mistake that. Many times people mistake warm temperature superconductor to room temperature, because even if the superconductor rates it, they will rate it 77 degree. They're not gonna say 77 degree Kelvin, because it's expected. If you're dealing with superconductor, you should be wise enough to know that. So you can give an idea. Liquid helium is very low, it's reaching 0 Kelvin. Then you have basically liquid hydrogen, which is a bit hotter, and then you have liquid nitrogen, and then you have liquid CF4 gas, chlorofluorine gas. So warm temperature is liquid nitrogen. Now that makes it awesome. Why? Only liquid nitrogen is needed. So if somebody asks you the cost of dry ice is expensive. Now liquid nitrogen, it's more or less the same cost. How the heck that happens? Here's the deal. You can, if you have electricity, That's it. That's all you need for liquid nitrogen. You can have big versions of these, what we call nitrogen generator right now. You can buy this. Heck, some people, some YouTubers have built it in their home. Of course, it's not efficient. It takes a lot of energy, but it does work. All it needs is atmosphere. Why? Because our atmosphere is upwards of 80% nitrogen. So now you might be like, can't I do that with carbon dioxide? No, because atmosphere's carbon dioxide content is barely 0.003 or 4 in some places. So in those sort of things, you have to understand, if you try to extract CO2 from atmosphere, yeah, your pump is gonna break. If you try to extract anything other than nitrogen, you cannot extract it from the atmosphere. But in the case of nitrogen, you can easily extract it. And nitrogen has also the another benefits is that it's flame retardant. Basically, even if let's say you build something that is hot, basically compared to liquid helium, it's hot, it goes to liquid hydrogen. Hydrogen is a flammable thing, it goes boom. So we don't want something that goes boom. Your MRI machine should not become a death trap. So using liquid nitrogen, it has multiple benefits. First of those benefits is that if it leaks, yeah, of course it's gonna kill you because of you're gonna suffocate to death, but it will put out fire. So it's fire retardant. So that's pretty awesome. So basically, if you have a cable and something bad happens to it and liquid nitrogen, it will not catch on fire. Inherently, it will not catch on fire. So that's awesome. And liquid nitrogen, you can simply build this sort of generator everywhere. So let's say your substation require, let's say 500 liters of liquid nitrogen. You brought it through a truck once, done, and then you have this generator running constantly just to refill it up. This is just there to refill it, and it does not require too much power. So this is awesome. That is why we are so excited about superconductors now. It's like liquid nitrogen is something that we can make at home. If you have a place where you have electricity and atmosphere, which you will have if you are in Earth, I'm assuming that you can make liquid nitrogen. That is the amazing aspect of it. That's why superconductor is finally becoming something that people are serious about, because of one temperature superconductor and liquid nitrogen. Now it's relatively cheap. Now when somebody says about superconductor, you have to understand there are hundreds of superconductor elements here, but each of them have their own pros and cons. For some reason, let's say you want to make a MRI machine, you have to make a magnet coil basically. Now that magnet coil can be made out of thick ceramic. That's very good, very high resolution. You're gonna get a lot of Tesla, but it's very fragile. So you build that MRI machine in an earthquake prone area, yeah, your superconductor is toast. So you have to understand that there are many ceramic options that allows us superconductivity in using liquid nitrogen, but there are different conductors for different need. You have let's say you want to make transformer that is running on superconductor, awesome, but let's say where that transformer would be. If that transformer is in case of a train, yeah, you have to make sure it's very resilient to temperature spike, very resilient to shocks and physical vibration, and many of these things are very brittle. That's the inherent problem with that. That's why even though we figured out how to make this, even though we figured out how to make the conductor, that's why we are not seeing it everywhere. It's very fragile. So you make a conductor, it's more like a glass rod, you drop it, it's done. So that's the next step to make a one temperature superconductor cheap, reliable. Once we have that, liquid nitrogen part is already solved. So this is our future. We're gonna see a lot more superconductor, and best case scenario, if somebody figures out how to make a liquid nitrogen superconductor running for basically a MRI machine, the price of MRI machine will go down drastically. That means more hospital will have more MRI machine. That will reduce the cost, give basically better healthcare. So that's amazing. I'm like, that's why I'm more excited about it. I had to go through MRI machine recently when I was dealing with my back issue, and it takes time. Like you have like a long queue, and we have to pre-book it, and it's a very frustrating thing. Now imagine you made it cheap. Imagine you made it like how cheap ultrasound is. Everybody can do it. Heck, you can detect cancer before it even becomes a issue. You're like, oh, go to MRI machine. Every 6 months, just go to MRI machine. It's that cheap. Right now, it's not. But if one temperature superconductor reaches its maturity, it can become that. So it's very amazing technology. It's not something out there has no effect on you. No, it has direct effect on you. If MRI machine goes cheap, our healthcare will become better. The undeniable. There is no fact in this. There is no politics here. It's absolute. So this was my presentation on superconductors. I hope you liked it or learned from it. In that case, please leave a like, click the ad shown in this video. That will directly help me. If you didn't like it, don't worry about it. You can press dislike button twice to show me your extra disappointment. And I would urge you to leave a comment because I reply to all of them. And press subscribe, press the bell icon if you're free. And as always, thanks for watching.